environmental programs at Uni of Melbourne. He also is Editor-in-Chief for Geomorphology. I don't know where you find the time. And in addition to that, as I mentioned, we do a bit of work together on the Victorian Coast monitoring program. So talking about the life of rocky cliffs, a lot of the examples from today will be taken from Victoria, one of the understudied coastlines of Australia. And with that, Dave, if you'd like to jump in, thanks.
Thanks, Jack. I'll say I'm co-editor-in-chief. There's a few of us, so I'm not doing all that, although, yes. One does stretch oneself a bit too much, I've found. Thank you, everyone, for joining today. I was going to, although I was originally planning on doing Milankovitch cycles, I decided, again, I won't do as much on that as I was hoping in this space here. And this will be more sort of an exploration, I think, of, because it's lunchtime, a whole lot of nice pictures and some ideas, but basically rocky coasts and really thinking how they evolve and some of the challenges, I think, and what we've sort of found. And very much what we've been doing here in Melbourne with the coastal research team, Rhiannon Pete, who finished their PhDs a couple of years ago, Runji, who is currently doing his PhD, he's in the last stages, and Tom, Jem, and Hannah, who did masters and honours with me in the last few years. So I'll be drawing a lot on their data and, of course, taking entire credit for their work in that space as we go in. And I think the Victorian coast is sort of interesting. On this sort of a classic Victorian sort of rocky coast shot. This is along the Great Ocean Road. We're coming into Lorne in that space along there. And it's an interesting space because the Victorian coast is actually, although the coast itself for Victoria, as Jack said, is quite unstudied. We barely know the actual measured wave height until recently. The rocky coasts have actually been quite a centre of exploration for almost a century now. We go back to the mid 20th century, Gill and Lang, Edwards, Hills. It was actually quite a centre for a lot of the debates that have been done on rocky coast, to such an extent that Gilshay back in the 1950s actually said there was a Melbourne school. So the rocky coasts themselves have actually really been focused on quite a lot of debates of the fundamental drivers of these landform systems, but also looking at the development, I think, of coastal geomorphology and coastal science in terms of what are we doing with Milankovitch cycles and sea level recorders as through platforms. And Eric Bird developed a lot of that. And then, of course, Wayne Stevenson came in just before me. Interestingly, though, even though it was described as a Melbourne school, there must have been some politics going on because Sherburne Hills, I've got a note here, 1971 wrote a paper in which he said there was definitely not a school and there was no collaboration between people in the work. So despite them being pretty much co-located. But so what we're looking at is really some of the fundamentals. But of course, rocky coasts aren't just in Victoria. I mean, that's a pretty standard thing to say. We're looking at areas where we have collision margins, where we have cliffs on the coastline, low sediment supplies, where we uplift hotspot type areas, where we're getting, but pretty much any area where we're not getting large amounts of sediment being deposited, we're getting these erosional landforms. And that's really the idea, is erosional landforms that are traditionally been seen as just sort of very passive features that just sort of sit there and don't do much, at least by the non-coastal geomorphologists, I think, in that area. And we have quite a range of forms when we look at rocky coasts. And so, for example, some here, this is the Glamorgan coast in Wales, I think the site of Alan Trenhale's PhDs in the, can't remember when he did his PhD, I think 1960s, in terms of that space, and a lot of work being done by Larissa Naylor and also Wayne, who's been over that way too. They're sort of macro tidal coastline, large amounts of block plucking occurring on that area. We go down to the coast of France on the English Channel. We get cliffs, we get nice sea arches. I think some of the impressionists quite like this coastline too. I couldn't quickly Google the image from it beforehand. But we're looking at chalk coast cliffs. In the case here with very little platform development. We contrast that to the New Zealand coast. Here we are on the Wairarapa, so on the eastern coast of the southern part of the North Island, where we've got a nice series in the case here of uplifted terraces and older Holocene and older cliffs now mantled by debris. And I think one of the challenges that's been a lot with rocky coasts is we've often tried to then sort of have, and especially as the discipline has developed, working out uniform models of coasts from different sets of locations. And I really feel that's a lot of areas where a lot of the controversy and a lot of the debates that still occur have their sort of derived themselves from that. As we found with surveying, I mean, there's not a lot of rocky coasts that have been surveyed. I mean, there's a lot more recently, but we can name most of the main sites that were still within site-specific locations, which have a lot of site-specific factors driving that landform evolution. And some of those original debates, I mean, they go back to the mid-19th century. What was his name? James Dunn, back in the 1830s and 1840s, as a US exploring expedition came into the Bay of Islands in northern New Zealand in the township of Russell and described what is absorbed as Hat Islands. And back in those stages, they were even part of that discovery of that expedition. Sorry, my words been fumbled for end of the week, was even the difference between the erosional level of a platform and the accretional. And they were trying to compare rocky coasts with coral reefs in this space. But the idea of the Hat Islands really has dominated a lot of the literature, especially what's sort of been termed the wave versus weathering debate, is when we look at these features, what is the main principal process that's driving it? Is it waves or is it weathering? And it was often for a while, I mean, still until recently, I think we're a bit over that polarized debate at this stage, but really seeing what is that main driver. And this is where Bartram in the 1916, 1920s, then produced his model with sort of weathering, of saying there was a zone of weathered rock that went down onto the platform, and that was then removed in the initial weathered zone, which was then eroded out. And one thing we had to look at when I was back based in New Zealand was Mark Dixon and myself, we wandered up to that area. It was actually over 10 years ago now. Ryan Paulick, who was a master's student at the time, and sort of reinvestigated the original Hat Islands of Bartram. And we can see here that they look still very similar, I mean, 100 years later. Rates of erosion there, it's actually a reasonably soft lithology, that, but we're still seeing almost exactly the same forms, and even some of the trees we can see have grown in that intervening period. But I think one of the important areas that was found at that time, but is also obviously within the global thought, was it really becomes the boundary conditions, I think, which is determining our platforms. And it's really important to think when we're comparing these things, so comparing like with like, I think is one of the areas which the discipline I so struggled for many years, of comparing processes from one area. So this is how shore platforms erode from the Great Ocean Road. Compare that to, apologies for my phone, compare that to, say, the Glamorgan coast, which is macro-tidal, very different wave environments, very different rock environments as well. So it becomes quite important to really contextualize our landform systems in those boundary conditions that they operate. For example, we have coastal barriers, we have regressive, transgressive barriers, we have different sea level cycles, we have different sediment components within those systems. The same applies to those rocky coasts. It's really saying, what are those boundary conditions and what's driving it? And that had been developed quite nicely, a classic diagram from Tsunamura and the work that was done in Japan, of just comparing a simple combination of the breaking force of waves versus the resistive force of rock. Effectively, in this space, we have very resistant rock, not much to erode, to very soft, down as we move left on that, and then increasing wave height. And that was then sort of parameterized in terms of this nice relationship between what would be a plunging cliff line, in the case here, shot diving off the edge of Lord Howe Island, on the northern part of Lord Howe Island, on the big steep basalt cliffs, in the case of that space, where we're in sort of an arrangement where, case here, the wave energy is reasonably high, but the rock itself is so resistive, it is just impervious to erosion. And as we soften the rock up, or we increase the erosive effect of waves, we then move into our shore platforms, our cut terraces, and then into different modes of that. Although I think I would say the type A, type B sort of binary classification, where the type B is a seaward edge, the type A is a sloping surface. We've sort of moved a bit. Platforms do form a continuum within those different type areas, especially once we start seeing what happens offshore. But that whole link of what does with your boundary condition, does your platform type, but it's also important in terms of what's your platform elevation. Where are we sitting on the coastline? Because of that determines where are the waves going to occur, how much energy is transferred across your system, and where will it get to the cliff lines, which in turn impacts your cliff heights at the back, your rates of erosion in that space. So an example here, another example from Lord Howe Island, back with Mark Dixon and myself in our PhD days. He was looking at the Rocky Coast, is seen here with one of the more igneous type lithologies. We're having a platform here at mid to high tide elevation. And if we swing round onto the beach just behind, we move more into the calcaronites. We have Quaternary Calcaronite sequences here, and we find those platforms are then formed at roughly low tide level. So simply within the space that we have in that area of simply changing the rock type with no change in wave exposure or wave energy, and no significant change anyway, we're having different levels of where those different elevations at which those platforms are occurring. And I think that's quite an important system of looking at these areas and looking at their future responses, as we see with sea level rise or change in wave environments, is it's those boundary conditions that they're operating in. It's obviously not appropriate then to infer rates of retreat simply because there's a platform. In the case here, our level of protection from wave energy is quite different if you're at high tide as opposed to low tide in terms of exposure during the tidal cycle. And one thing that was done as part of that work, it's a nice classification Mark led in the case here, is even comparing the types of platforms we found on Lord Howe Island. We have our type A, type B. We can combine them into different types. Actually, got an A, B, C, D, E in the case this space, just simply relating the Schmidt-Hammer value, the simple compressive strength, the hardness of the rock, versus the joints. Hard rocks, higher joints are more erodible. So I could almost say this is a resistance here. This is almost erodibility. And those platforms themselves then move into a continuum. We have in here the Mount Lynchburg basalt. That's what we're seeing in this space here, where we're diving off on that space. We're barely getting platforms, or they're very narrow in case of that section. We move into the North Ridge basalt, which is the nice red one in the background. And then we have the calcaronite down in that space. So quite an important, just broad landform scale driven by those boundary conditions, or that geological control, as we tend to conceptualize the level of platforms in that space. So it seems quite obvious in terms of one level, but it's quite important when then transferring those results from one site to another of what we're looking at. So simply harder platforms tend to forward higher and also often are narrower. But if we start to unpick the level of structure in terms of that space of how does it do at a more site-specific level, so we're moving around the example of Lord Howe Island there, comparing between sites, we can also see the role of structure also driving a lot of the landform evolution, even at a specific area. And the case here, we're at Shag Point down on the Otago coast, or on the east coast of the southern island of New Zealand. We've got a very nice, consistent sandstone coming across our platform here, a little seaward cliff dropping off the side. But we've just changed the structure within that space. This cobblestone area is just a more highly jointed unit within those platforms. So where the platforms are less jointed, so just have a standard survey across the top, 20 metres, 40 metres across that space. That's high tide, mean low tide, mean sea level there. Our platforms are affirming at high tide level. That's what we're doing. That's the elevation at which they're at. And we can see our cliffs in the back are actually a lot smaller in the case there. We move further along that section. This is only a couple of k's length of this coastline. When we get to the more jointed part, there's Mark there wandering off in terms of this space, we can see that the platforms there are actually lower. In the case here, these platforms form at low tide level. We have the same rock type, we have the same compressive strength, they're pretty much the same, well, I'll say similar rather than the same wave energy, but that simple change within the structure has changed that elevation. And this is really obvious even in the space here, right across that center of this shot, where we've got our unjointed section there, and we come down in this space here to the more jointed area. And this has a direct effect on land management. The houses behind, and I haven't been down there for about 10 years, but pre-COVID, they were selling quite quickly, but they're also eroding. There was actually letterboxes left along that space where the cliff had actually eroded back. And the areas where there were still houses were in the more resistant space there. So it directly fed into the current rates of retreat and the housing developments that were along that section of the coast, simply by the structure of the rock. The platforms were lower, those cliffs were eroding back at a much greater rate, but really just derived from the boundary conditions. If we go to the other extreme, I suppose when we're looking at ones, we also have systems where the rock is so soft that we don't actually have platforms at all. And I think that's an important distinction when we're looking at our rocky coast cliff lines. Rock platforms really occur within sort of almost a sweet zone, I think, in a space on our coastline where the rock is resistant enough to allow a feature to be formed, but soft enough that it can still erode, because our rocky coast is forming through a landward cliff retreating at a quicker rate than the seaward edge, the seaward cliff in terms of that space. So we're getting an erosional remnant, but that erosional remnant itself must be resistant enough for the wave energy. So here we are on this, is along some of the areas Jack and I are actually working on now, part of the Victorian Coastal Monitoring Program. This is the Anglesey cliff lines, and this is made up of a tertiary mud, best way to describe it in terms of that space. But we've got quite high rates of retreat. The sections along here, we're getting 30 metres of cliff laterally, 10 metres in, peeling off at very regular intervals. But the main reason before that, it's a rocky eroding system, but it's resistant enough to hold up a cliff, but it's not resistant enough to allow a platform to form. We've got a few rocks here. That's more cliff debris flow falling off, not debris flow, but debris talus that's remained. And our platforms on it might be a tiny platform there in terms of space, bang in the center, but the rest of that coastline, because the system itself is not resistant enough to maintain a platform feature. And as a result, these cliffs are eroding very quickly as well. And this section here actually has been now closed off because of that cliff hazard. And we observe the same round in New Zealand as well. This is coming round the Taranaki-Wanganui coastline. So we've moved to the west coast of the North Island, very much muddy sediments. Well, I suppose they're rocks, but get onto your definition, I think, of what you can define as a rock. If you can stick your finger in it, well, is it a rock or not? But we definitely have a lithology that's sitting in that space. We're forming cliffs. There's enough resistance to hold the cliff, but there's not enough resistance to keep that platform feature within that wave zone. So we're really seeing within the platform systems, it's the boundary conditions that they're operating within and how that boundary conditions allows a morphology to form. And one of the challenges I think we have is really a classic scale challenge. I quite like it. It's a great introduction for lectures, temporal and spatial scales. I think it's really critical in terms of this space, but it's really marrying landforms that are evolving over multiple sea level cycles in some cases. We're seeing here, we have a coastal terrace. It's not a short platform, but it's still an erosional feature with deposition on top. This is the, I think this is the east coast of the South Island of New Zealand coming down towards Kaikoura. But we're looking at scales of studies of modelling something like that, or comparing it then to individual rock falls in what we'd say would be Anglesey in that previous shot. And that's one thing I think we've struggled with in terms of how do we measure and how do we do predictive values of landform systems which are operating over long times, of which our observational period is quite small. And of course, one approach to do that is the modelling, some classic modelling, single line modelling that's been done by Alan Trenhale. And there's been some great work coming out by some of the people in the audience here, looking at these longer term cliff models and trying to marry the different levels of scale that we actually have beyond what is an observational scale of what we see for an individual landslide, as opposed to total landform evolution. And doing that, so we have modelling at that level, but on the other end of the scale, there's also a lot of work done really on the micro scale, the micro erosion meter. An example here of the MEM from one of our sites down on the Great Ocean Road at Marengo. So it really is one thing we can do, the micron level of scale at one space, numerically model the other scale, but it's linking those areas, which I think is a real difficulty. And I think it's still one of the big challenges, I think, that we're all attacking, I suppose, in the level of what the field is. There's sort of a recognition now that our site-specific values are important, but they are within the context of those boundary conditions. But how then do we link our sort of principal methods to get across to the landform evolution? And it's a classic problem within geomorphology and scale. We need to know for climate change resilience, what are we like in 100 years' time? Well, how do we link our larger scale mappings with our more field-based measuring in terms of that space. And this is a review, Martin Coombs and I think Derek Motorshead, I think, were involved in this one. Apologies if I've got the wrong author list here. But we sort of identified a potential one. This was looking at Earth surface processes and landforms previous studies. So there's almost a knowledge gap sitting between our repeat surveys, our laboratory simulations of maybe within decades and hundreds of kilometres. And we could definitely have a good argument whether that knowledge gap is filled or not. But I think it's a key space of trying to link in the mapping and the meta-analysis back to what might be instantaneous scale landforms. I like to think of it as an example, as I was thinking further about this, it's almost trying to infer barrier scale evolution from just a single wave sensor current meter in your bar rip sequence. It's possible, but it's quite a difficult translation to then make. So hopefully I'll try and link some of that maybe as I ramble on through the rest of this talk. What do we have in? So basically when we're looking at shore platforms, and I'll focus more on shore platforms for this talk, is we're really looking at these intertidal features, and shore platforms really are intertidal landforms. And they really are sitting themselves between that sort of low tide line and the high tide line, where we're getting emergence and submergence over the tidal cycle. This case here is an example from Whanganui Inlet. So we're up in Westhaven Inlet, Whanganui, tip of the South Island of New Zealand, but within a large structural estuary system here. And I quite like this platform system because it's really one which I'd say is at the boundary between where platforms can form. And in fact, as we move out along the platforms, they actually transition with depositional mudflats. And really the only reason we have the platforms here is it's again the local boundary conditions. The rock type is very soft. It doesn't form platforms on the open coast out here. That's the west coast. We're in the roaring 40s in the case of this space. But where it's small enough energy within a structural space in here, very fetch limited, there's just enough wave energy to erode out the platforms and erode them down. And we're now moving, it's eroded down till it's then preserved by the mudflats that then are accreting across the top. And these platforms can continue off moving down behind these areas. And there's a nice sort of old hat island there. But one thing we do know with the platforms, and this has been done with some quite great work from Cunard and Trenhale with their experimental work at the University of Windsor and some of their sites in Bay of Fundy and those coasts, and also some of the great work Bob Kirk and Wayne Stevenson have been doing with the excellent microerosion meter record that's on the Kaikoura Peninsula. But really what we're seeing here is sort of wetting and drying efficacy, and I'll take a bit of artistic license as a speaker and sort of say erodibility, erosion intensity, or something like that that we're seeing in that space. And the microerosion work from Kaikoura, we're looking at quite a mudstone environment there, lowest high tide to highest low tide, that broad thing. Some of the experimental work that Alan did is looking in lowest high tide with some of the more resistant basalts and some of the sandstones he was using there. But I think this is an important concept within this space, because we think of shore platforms as effectively being static features at the sea level. Whereas we think of them lowering through the tidal zone as they move down from whatever's high and being eroded, their actually rate of evolution, the rate of landscape evolution, is actually changing quite significantly. They're sort of speeding up. You can imagine as they enter the intertidal zone and then slowing down as we move out of the intertidal zone. So trying to model these in terms of a landward retreat becomes more difficult if the rates of movement of your actual surface are changing through time. And I think that's an important concept within this space of thinking how dynamic these platforms are. And it's a classic mistake that's often made within coastal management is people build a seawall on the edge of the platform and they stop, and then the platform continually lowers under the seawall, and the seawall eventually fails as you start getting gaps underneath, because they are actually dynamic. And I think it's an important takeaway message is thinking the dynamic nature of these surfaces really it's almost not as fast as a sandy beach, but they are actually dynamic in that space. So one thing we can start to look at when we're looking at the longer term erosion, and here's another shot from the other side of Lorne, beautiful platforms with a ramp coming up, little sand veneer, and really not much of a seaward cliff in this space with these platforms. So we can really try and start to unpick, well, how is these rates changing as we move through the actual intertidal zone, sort of a space for time type substitution. And really what we're looking at here, I'll be drawing a lot on this space from the fantastic microerosion network, networking microerosion meter here, that was set up in the late 1970s along this by Gill and Lang. I think it was actually Edmund Gill's last paper. And here's Runji, and this is one we're still actively doing. Here's Runji Yuan working on his masters on that site with Wayne Stevenson in the space here. And it's a really important site for this one because we can now say that I can claim, I think quite reasonably well, some might correct me in questions, that this is now the most continuous, this is now the world's longest continually monitored intertidal shore platform site, courtesy of Kaikoura deciding to uplift itself a few years ago, and those MEM sites that Bob Kirk installed just a few years before this were then done. But it really is a fantastic site because of that longevity we've got and a variety of sites we've got around the area. And I really have to give my hats off to Wayne in this space, because while he was based at Melbourne before me, it took him a while to trace down both Gill's original notes, the sites themselves on the platforms, which are still there. But I think the best part of it is finding the actual original MEM and the calibration plate buried in the field store at Canterbury Uni. So once we've combined all that, it's why we've been able to keep these platforms and these sites going. But when we've gone through that, so we've worked out the mean annual scale of erosion for the past 4 years. It's around 0.31 millimeters per year. So 0.31 meters per 1,000 years. We have the last 7,000 years, potentially 2.1 meters of downwearing during the Holocene. But of course that starts to, and this is one of these scale issues. If we take a millimeter per year, we scale up to the Holocene. The question then becomes, well, why do we have platforms here if we should have lowered these by 2 meters? Were these 2 meters higher? Was this 2 meters higher and cut down? How much has it cut back? And that's that scale issue of moving between individual grains and up to the landform scale area. So to look at some of this great MEM record in this place, and I'm going to liberally steal from Runji's masters and his current PhD, is we have quite a good distinct distribution of MEM sites right through the intertidal zone, but it does drop off as we move down to the water level. There are most of them concentrated in the upper portion, the central portion, around mean high water, mean low high water, and we have some that go down to mean low water. Only a couple of the original sites have been lost of Gill's work, and unfortunately they're the ones down in the base here. They've actually been buried. In fact, he never found some of the original ones he actually installed due to post-sea level, not post-sea level, storm cycle movements buried his actual sites in the couple of years when he originally was measuring them. But I think from these sites, we can start to go back to these levels of where is the maximum wetting and drying efficacy, the erosion space there, of starting to say, well, how does this link in with our platform systems? So as part of Runji's PhD, which he's been working very well at publishing as he's moving through the system, is we've got our erosion rates in the case here for each one of the MEM sites done with height above mean sea level. So within the upper splash zone, so we move really above that supratidal zone, we're up in here, we're sort of almost getting a pretty all over scatter of points within that. But once we enter that intertidal zone, we're starting to see that erosion rate is actually increasing as we move down towards the mean high water mark, and then decreasing as we move down towards the mean high low water mark in the case that space here. And that's quite, so it's really seen as the platforms are starting to enter the intertidal zone, is where slowing down as they move up, but then speeding up in their downwearing and then slowing down again. So inferring our rates of change through time become difficult because our rates of erosion are actually significantly different as we move along these areas. And interestingly, for the lawn platforms, is we're actually having this sort of peak here is sitting highest high tide. We're actually bringing it out more up here than necessarily was seen in some of these other platform sequences. And I think this hasn't been analysed, but some arm wave, I think it's probably got to do with the resistance of the rock is actually what we're seeing in a lot of spaces. The advantage we have with these sites is the sandstones of the Otway Ranges, the Cretaceous sandstones there are reasonably resistant in that space. So they actually have preserved the MEM record, which of course sets up another problem with where do we get our MEM records from, especially the longer term ones. But if we go back to the actual sites themselves, once we're in that sort of spray zone, we're starting to get a lot of almost randomness of our erosion rates, not really related to the elevation that we're seeing. So it started to give us an idea of, well, what are the processes driving this system? What is actually I mean, we're looking here at granular scale decay. I mean, that's how our platforms are eroding, at least this stage, is we're having individual grains moving off. So Runge, as part of his masters, then looked at this site here, which was installed, one of the ones Wayne installed a few years before. So we reanalyzed that space. We've got some very nice supratidal honeycomb weathering. There's our intertidal platform moving across. It's about high tide elevation there. So we're definitely out of the wave zone, except in the most stormy periods, we get some wave splash. A nice one to do continual measurements. So what we're just seeing here is the MEM site. The probe wasn't long enough to get the entire area. The probe down a bit in one corner. So we're really down at the micro scale here. We're staring straight at the platform. So our scale red here is 0.3 millimeters down to minus 0.3 millimeters from there. So we're only looking at movement of 0.6 millimeters. It's not a lot. We're at the grain boundaries. So we have the dates, 8th, 9th, 10th, 11th of November, and the times coming across in this space. And we see there's a lot of dynamic in that surface. That's what we're actually seeing within this space. This surface is going up, in the case of this line along here. We're moving ourselves up by 0.6 millimeters over hourly cycles. There's a ridge of high, it's gone down, it's come up, it's gone up a bit more, it's gone down, up, down, and we're getting this cycle moving across this space. And I think what we're actually observing here is we're observing that effectively it's the instantaneous sediment processes we're actually seeing. This is the granular decay that we're actually having a look at. So a bit more as the multi-day differences between the different sites. Again, we're looking at the same thing. I've just blown this up to get a bit better view of what we're seeing within that surface. So the surface itself, I mean, it's not perfectly flat. I mean, you can tell that by just looking at the hummocks going along, but it's also dynamic. And I think that's the important part. This is what we're seeing with the erosion. And through the measurements that were done here, we can then say that our overall platform volume change has actually decreased through time. And this isn't through granular decay. This is the mechanism, I would say, that initiates granular decay, but there wasn't any erosion of this surface in that space. No grains were observed to come off from that platform area. So what we're seeing here is shrinking and swelling of the platform. And that was something that was originally described by Wayne, part of his PhD, of noticing that within the Kaikoura Peninsula in that space. So at least for along this area on the Great Ocean Road, this is Marengo, so we're down towards, down the southern part of the road. For at least for this site, we then get a period within the morning of shrinking, then the afternoon it was swelling, and it tended to stable off during the evening. And we saw these cycles moving through time. I mean, impressive one was it's actually measured right through. This is actually through midnight, 2 a.m., 4 a.m., going out measuring these areas in terms of that space. So I think this really shows when we look at the micro erosion for this site, on average per year, 0.3 millimeters of down wearing of that space. We're not seeing it in this case. We're seeing that swelling of the surface as it goes down. So I can imagine our platforms through time move swelling, shrinking and swelling. That causes you granular decay, and through time, that's then moving down through our surface. This is basically our instantaneous scale landform evolution. But you might say, when you're staring at the platform, how representative is a site that's that big? I mean, it's in that. In fact, no, I don't have the MEM in my office right now. Something that's that big, but we're inferring that for a feature that's that large. What is the representation? What's the spatial representation of that within that area? So it actually run well. As I said, I was going to liberally steal my students, my student collaborators' work here. Runge then managed to go across and run using structure for motion processing. So I missed Javier's last talk last time for other meetings, so I apologise for Javier if he's here. But we did the same structure for motion methodology that we've been using for the Victorian Coastal Monitoring Program, and everyone else would probably be using themselves, and ran these over the platforms with the imagery here. And we can actually pick out, and this is just the imagery, and we can see each individual MEM site to really then quantify, well, how representative is that site of the entire platform? And that's quite important, because when you install, there are methodological standards when you install your MEM. You tend to install them on nice flat surfaces that you can put a micrometer on top of. Is that really representative of the area? Are we biasing our MEM-based data to areas which will only have granular decay? So to test this out within the sites within the GILS MEM network right around Victoria, around structure from ocean. So here's our slope model of the area. We're going from obviously very high to very low slopes. Got our rock areas along here. So this is this site, there's this little rock. It's really a joint line. Some faulting is also going through in terms of this space. And then we have a roughness measure across the top. So quite variable within this type system. We actually found for in the background here for Marengo is the MEMs actually represent around about 73.2% of that site is measured by the MEM. So the MEM here is actually quite representative of the platform area. And from some of the other sites at Jump Rock, which is one of the other, oh, sorry, I got around the wrong side. 52% at Marengo, that's still not too bad. At Jump Rock, it was actually 73% represents that space. So we can start to then say with our spatial scaling of saying, well, how representative are we occurring? So we can say quite confidently, these downwearing rates apply to half of the platform in the place here. Of course, the next question goes, well, what's happening in the other half? Just because it's not morphologically similar, maybe it still occurs. But interestingly, as we move towards the MEM surface versus the non-MEM surface, we're actually coming down towards the seaward edge of the platform, which of course is where the wave action is actually happening. So we are having other areas and other concentrations of waves, and waves can, we do know, tend to work through lines of weakness. Joint lines, fracture lines is where waves go. So part of what I've done is then looking at wave type areas. So this is Tom Savage as part of his master's project. We installed a whole lot of wave sensors across platforms at, this is near Inverloch, so on the further away from the Great Ocean Road, but it's actually the same lithology that we're seeing. A standard line of RBRs being installed across here. Tom looking very happy. His smiley shot made a faculty brochure just to keep him extra embarrassed, I think, from that. But we also extended this down into the offshore zone. And this was with Hannah Kowalczak, who was also doing her master's through Lund University in the case there. So really starting to see, okay, well, we know what the sub-area, the wetting and drying is doing, what's happening with the wave dynamics. They're the stuff that's causing the eventual, anything that loose up gets washed off, but waves can also pluck. And the case here on the platform, this will be very familiar to a lot of people who put wave sensors out on shore platforms, as we saw a nice transition across the platform from P1 at the edge, so across here, I think that's P3 and probably P4s at the back, the case there, of a transition. So we have our spectral density through 2 tide cycles, low tide it's dry, high tide we have the water, and we're having a transitioning as we move across the platforms. We have a loss of our gravity frequency waves, they're slowly decreasing, and an increase in the infragravity peak as we move across that platform. And that's been well described by the work of Mark and Wayne in New Zealand and Hiroki, the late Hiroki Ogawa, with his PhD in terms of that space there. A really nice pattern of wave transformation. But in the case here, we can see in the background, how far offshore does the platform actually extend? Is it really just an intertidal feature? What is occurring as we move further offshore in this space? So Hannah, as part of her PhD, here she is here. We actually then installed the same RBRs in a transect down the front of this platform and down what I would actually term a seaward ramp. So we went down from around about less than 5 meters down the ramp and then offshore into the rocky areas further off. An interesting thing we found, so this was a co-deployment. This is the area where we had the RBRs on the shore intertidal platform through the whole deployment over, was about 10 days in terms of that space. And we got reasonably good waves coming up to 2.5 meters offshore in terms of that platform. And we're seeing as the waves are coming across that platform, they're progressively decreasing in height as we're dissipating that energy on that rocky surface. But interestingly from that is when we see, so I've taken just the landward-most one, the one at the uppermost part of the ramp, it's about 5 meters water depth. If we actually look at the infragravity wave variance in the case here, it's actually starting, interestingly, we're actually getting a bit of a tidal signature in this space. So we just have infragravity frequency variance here with tide cycle. And we're finding as the waves are moving, tides going up, we're getting a peak within that infragravity sequence at every high tide. So I think what we're seeing through here is two processes, both infragravity generation as waves are shoaling across that ramp, because the ramp here is actually quite, I mean, this is only a slope of about 3 to 5 degrees. It's actually quite flat. I mean, sometimes more akin to almost a beach environment here. That we're seeing infragravity generation, especially as we move into the more shallow depths. But we're also getting escape of the infragravity mode energy from that shore platform at high tide. So it's escaping back offshore in terms of that space. And really, what we're starting to look at is saying, well, okay, if we're getting that generation offshore, well, really, how far offshore is our shore platform actually extending? What is that active landform? I mean, we tend to think of them as an intertidal feature, but I'd say we should maybe be more starting to think of them as being subtidal as well. Potentially, I'd say going down to wave base might be an area, or at least where we can say there's active erosion of that bedrock. So just a couple of examples here from the fantastic Future Coast LiDAR from DELP, our Environment Department here in Victoria. So good. I mean, it takes hard to actually, that's low tide level along there. In some spots, it's actually difficult to spot where sea level is because of the nature of that. And just a slope model running along the top. But we can see as we go along these platforms, we get quite different morphologies from this sort of more sheer seaward area to more a seaward ramp coming down in that space. And this is a comparison that was done between a few of the classic sites. And I'll just say this is Kaikoura of just literally stealing people's data in the case here and mapping it to the same scale. We can compare some of the areas from, say, Marengo, where those great MEM record is, to the areas in Auckland, to the classic platforms at Kaikoura. And we see our seaward morphology is being quite variable. And I think that means our overall wave dynamic is also quite variable too. And this is that area of translation between sites. What are the different types of platforms we can actually see? And I'd say from looking at the area, we have almost 3 different types of seaward morphology. And I think this is important because while we're diving and installing the probes, there's actually quite a lot of active abrasion on that seafloor. This is off Cape Patterson. So if we come down in this space, we're about here. Where are we on the ramp? We're down in about this section here. We're in the upper part of the ramp, about 5-7 meters depth. But that surface here is perfectly lovely, flat and smooth. There's active abrasion happening on this platform. There's active work being done on that area. And that one plan, I think it'd be nice to get some micro erosion meters done subtidally. I think there's only been one study I've noticed that someone's managed to actually do that. But the wave energy itself, to sort of do our full life cycle ones, then does really affect people. And I just sort of finished off in the last 5 or so minutes, I think, of really then saying that impact of the waves. It's a geomorphic process, but it's also a significant hazard. And this is for rock fishing. This is actually waves breaking over one of Gill's sites. This is the Jump Rock on Lawn. So we actually have one of the MEM sites is actually on that rampart. But the same wave energy, of course, it's doing work, is also affecting rock fishing, which has really been done as the most dangerous sport in Australia. It's actually done is rock fishing by sort of a sobering simple body count in terms of that space. So what I did in this space was a collaboration with Surf Lifesaving Australia, was really starting to say, well, okay, how can we then start to develop different areas in terms of that space? And I saw Andy Short was popping in earlier on. Jack mentioned as he came in, sort of following some of the ABSAT, the Beach Safety Index, of how much can we take these morphological factors and apply them to shore platforms. And simply doing a simple relationship, I think, between the platforms lower, you're more exposed to waves. If it's deeper offshore, more waves can get in. Very simple relationship. The idea was to get as simple as possible, can then work out a potential morphological risk factor along this space, along these platforms. And that's what we've done here with the larger ones here, is simply just a traffic light type area. Red's more risky. So we come across our Jump Rock site. So there's our light sites there. That little orange circle there is right in that spot there. So it's where the waves are coming in. So that's really looking at and trying to then here put it in with some wave modeling that was then done as part of a different project, which I can't claim any credit for. But I think that's important of saying we take these morphological factors, we're looking at the ways driving landform evolution, but it directly affects that safety and that management of where we're seeing, because it's the morphological features and that energy, it's removing rocks, but in a lot of cases, it can also remove people. And this formed a lot then of some of the work of Pete Kamstra, who is PhD on this area in terms of this space, of then saying, well, okay, once we have that hazard knowledge, how do people then interact within this space? So as part of his PhD, he became a rock fisher. He moved from Canada to Melbourne, did his master's, and we managed to convince him to stay for his PhD. And he became a hardcore rock fisher through the project in terms of that space. But what he did, and this is Little Bay, southern beaches of Sydney, was really looking at some of the most hazardous rock fishing spots in the country, and then saying, where do people go? But importantly, how do they view the geomorphology? How do they view the wave processes? So this is some of the actual data. The mapping in the background is what people mapped perceptions. So they map that wave overtopping occurs in these areas. The brown area, they said, is safe, and the pink area is a channel. And the case here for this platform, a lot of people get caught in the channels. The waves come across and then wash them along, or they slip. It's more a slip rather than a wave process. You slip and then the waves sort you out, is really what you're seeing in this space. So we map the perceptions and then physically where people go. So people set the fish on the line a bit higher up where they don't see waves. They run quickly through the channel and park themselves on the edge of the platform in that space. And then, of course, no, they don't. There is a nice little warm spot here, right in the middle of the most dangerous part, the wave overtopping and the channel. And yes, that is definitely the most dangerous part. But a secondary finding which Pete actually got from this work was really, these are the inexperienced fishers. The ones who haven't been to the site before, go to that spot because it looks like there's good fishing offshore. The experienced people don't touch it. They don't go down there unless it's really calm. So this starts to go into what we call experiential understanding of risk, of how does the experience then of risk map onto that, because we're seeing where people go. And we can link this straight to wave processes. So through this same interview process that then Pete conducted was really seeing where do the inexperienced view risk as opposed to the experienced attuned risk. And you think yourself, where do you stand on the beach? When do you go out? And really was finding it was sort of a spatial. The more experienced you were, the more offshore you looked at. But you relate that into wave dynamics, into wave heights, you start to move into what chance do you have of spotting the big wave? If you're staring at the bottom of the platform, you're going to spot the wave crest coming in, it's on top of you. So it's an important area of then the risk back into the wave area. So I think to sort of summarize a random, hopefully not random, but a level that's cycle on platforms is we're still looking at how do these evolve, what are the processes that drive them, but it's couched within the boundary conditions, I think, of the time, of that exact site. And that affects everything from its landscape evolution to the hazard that's we're actually seeing. And I think one of the things that moving forward, and is now been happening a lot more, is one of the areas we now have, I think we now have the technology, is really starting to date the bedrock. And that's been the one thing that's been missing, I think, of filling that gap in that space. We're now getting the longer records, the longer timeframes of scientific study, but now we're starting to get with the various cosmogenic isotopes and those type methods, we're now getting the ability to directly date the platform. And I might stop there. Thank you.